right. Here we go. Put your phone away, get your notes out. We're going to do some exciting stuff. We're actually going to skip problem number 3 because Mr. Shadio told me that neither the AB calculus nor the BC calculus deal with denominators like we have in problem 3. So we're not going to mess with it. We're going to just jump right on to 4. And it says match the figure with the function and then make some observations. Okay, well, we don't have time to graph all of these things. So let's kind of look at the window that's established in our pictures. So let's just kind of look at those graphs. And let's set our calculator up to match these. So what does it look like the x's, x-min and x-max are in all of these graphs?
-5 to about 5 or 6.
Okay, so let's just do that. So let's set our x-min and x-max, just match what's here. And then what about the y's? Okay, let's do that. And then let's just graph the first one. Okay, let's just graph the first one. And see if you can match it to one of the multiple choice. Yeah. Well, I'm. Okay, see if you can match that first one. All right, did you match it? Were you able to match it? You think it's which one? C. Okay, now I want to talk about this for a second because like I said, we're not going to have time to graph each one of those. We're supposed to be able to tell from the equation which graph it matches. So let's talk about this. Now, I have sketched in the line x plus 3 here. Any ideas why I did that? Braden?
Because y equals x plus 3.
Okay, and why did I kind of ignore all the other stuff? Ben? Okay, so when I look at these fractions, as x gets really big, as we head out off the page, what happens to these two fractions? As x gets big, they get really small, right? And eventually, they become so small, they're like zeros almost. Would you agree with that? So when x is a big number, this part of the problem isn't really involved, and this is all I basically have. So this is my end behavior asymptote. Remember we talked about slant asymptotes before? This is your end behavior asymptote. Okay, so the curve, as it goes off the page, should be going at kind of a slant. Now, this tells me I have an asymptote at -1, vertical asymptote, and an asymptote at +3. You know that already, right? We know because we've graphed a lot of these things that on one side of the vertical asymptote, the curve is going to be going up, and on the other side, the curve is going to be going down. You can actually tell that from the equation. This sign right here tells you which way the curve is going on the right side of the asymptote, on the right side of the asymptote. So, on the right side of this asymptote, the curve is going up. On the left side, then, it is going down. On the right side of this one, on the right side, the curve is going down. And on the left side, it is going up. Now, I don't know what else is going on in there, but they've already drawn the graph for me. So I just have to find a picture that has that kind of behavior. So you said it was which one? C? So on C, I have to be going down on the left side of this asymptote and up on the right side. That looks right. And then on the other side, I'm going up on this side and down on this side. That looks right. So I can actually match these graphs without sketching. Let's try the second one and see if we can do that. Actually, let's go down and do like this one. 2 plus 2 over x plus 1 minus 2 over x minus 3. The second one from the bottom. So let's talk first about its end behavior asymptote. What's its end behavior asymptote going to be? Y equals 2. So this one isn't shooting up diagonally. This one is just y equals 2. So as it heads off the page, it's leveling off. Okay, now it's got a vertical asymptote at -1 and at 3. Oh, these all have the same asymptotes. But tell me what's happening around this asymptote right here. See that plus sign? That tells me on this side it's going up. This tells you the behavior on the right side of the asymptote. So on this side it must be going down. And then over here, for this one, we're going down on the right and up on the left. So now I got to find a picture that kind of matches that. Remember, it's leveling off. It's not slanting like this first one was. It's leveling off. Is it A?
Yeah.
I think it's A. All right, let's try one more. Try, I guess try the third one, the number 3, or the third equation. See if you can match that up without actually graphing it. David?
I got F.
Ooh, I didn't, but I could have made a mistake. I was doing it without drawing it, so it's being in my head. Let me double check. Anybody else get F?
I got E actually.
You got which one?
E.
E. I actually think it's D, and I'll tell you why it's not E. E, first of all, the asymptotic behavior for D and E is the same. Would you agree? But look at the end behavior of E. It's really hard to tell on these graphs, but it looks like that's leveling off, which means its end behavior cannot be x plus 3. So I think it's D, because that end behavior is going at a slant. Do you buy that argument, David?
Yeah.
Okay. It's hard to tell from these pictures, I agree. But what I want you to come away from this with is the notion of how the end behavior looks, which you already know that, and then this behavior on either side of the asymptote. Then?
So with the end behavior, that's not like an actual asymptote, it's just how it's gonna look at the very large numbers.
It actually is an asymptote, yes. But it is an asymptote that reflects how it looks at the very large numbers. So remember, horizontal asymptotes, also known as end behavior asymptotes. Horizontal asymptotes are special versions of end behavior asymptotes, are not asymptotes in the middle of the picture. They can be crossed in the middle of the picture. So you'll remember, I think we even graphed some before where we had things that looked like this. I'm making that up, but you know, they can actually cross in the middle of the picture. They cannot, at the ends, they will approach. That's where the curve is going to go. Yeah. Yeah, so vertical asymptotes are never touched. But end behavior asymptotes are end behavior, not in the middle. Yeah. Okay, all right. Well, we have one more partial fraction to do. I'm not sure why I stuck this one in here. Maybe it's interesting. So let's do it. This is review from last time. Then we're going to do some review graphing. Then we're going to do something amazingly fun if we have time. All right, so who remembers how to do this problem? This one's a little bit, well, I think we did one like this yesterday. What do I do? Philip?
You split it into A over S plus B over X squared plus C over X plus 2.
So Philip remembers, and I hope you all do, that when there is a repeated factor, like x squared, something twice, we have to include a partial fraction with the factor all by itself, and then with the factor as a square. Remember that from yesterday? Now, the order that Philip wrote these is not important. You gotta have 3 factors in any order you want to write them, and those have to be the denominators. All right, what happens now? Now we will get rid of the fractions. So basically what that means is I'm going to be multiplying everything by x squared and x plus 2. Okay? So 4x plus 4 equals, all right, now cancel carefully. Canceled carefully. Now I'm going to go ahead and do my distributive. Stop me if I made a mistake, please. Now what? Who remembers where we go from here? Philip?
Make your 3 equations.
I make my equations, and I make my equations by looking at, okay, now wait, I've got x squareds on that side, but I don't have any on this side. So what's that equation going to look like?
Ax squared plus c, ax squared plus cx squared equals 0.
Okay, but I don't even need the x squareds. So 0 x squareds equals a plus c. Does that fit everybody? Remember, your variables are actually a, b, and c, so leave the x's out. All right, now you got 4 x's, 4 regular x's. So that's gonna have to equal 2 A's and a B. And I think that's it, isn't it? And then 4 is also going to have to equal 2B. This is what happened yesterday. This is like wonderful, because what does this tell me?
B is 2.
It tells me B is 2. And if B is 2, then A must be 1. And if A is 1,
C is -1.
C is -1. You're not done. The answer is 1 over X, your A over your X, plus 2 over X squared, minus 1 over X plus 2. There are your partial fractions. Remember, your job was to find the partial fractions. You're finding the fractions. So your answer is the actual fractions. Got it? Okay. The next part's review. We got a couple of review problems here. We've done these. We kind of just talked about a little bit with those graphs we were matching. But we need to graph this rational function and include all of its asymptotes and intercepts. This look familiar? Oh Lord, we did this a long time ago. Who remembers anything about how to get started or how to do anything? And we're not going to use our calculator. So Tyler, what are we going to do first? We're going to factor everything. And what are we especially on the lookout for?
Things that cancel.
Things that cancel. Because if we cancel, not only does that make our problem smaller and more manageable, but it puts a hole. Do they remember the real name for a hole? What do we call those? Removable discontinuities. A hole is a removable discontinuity. Okay, well, I got one. So basically, this is what I'm graphing. But I'm going to have a hole where? Where is that hole going to be?
2/4.
It's going to be where X is 2, because that is the factor that canceled out. That's the X value that canceled out. And if I plug in 2 to get my Y, the hole is a point, I get 4/5. Are you all keeping up here? Doing this kind of quick because we've already done all this. So 2 4/5, right there it is. Now, what can you tell me from this, from what's left? What else can you put in the picture now? Philip?
The vertical asymptote is -3.
The vertical asymptotes at -3. Remember, always and forever, kids, vertical asymptotes are where you're undefined, and you're undefined when your denominator is 0. So we got a vertical asymptote at -3. All right, Madeline, I saw your hand up. Did you remember something else?
The horizontal asymptote would be 1.
It would be 1. How about intercepts? Sam?
Y-intercept would be 2/3.
Perfect. And Sam got that by plugging in 0, because if you are a y-intercept, your x is 0. And then where's my x-intercept? Don't be confused.
-2.
What gives you 0? What makes your answer 0? -2? Yeah. If you put in -2, this, which is y, equals 0. So you have an x-intercept at -2. Now, based on this, can you sketch it? You can always plot more points if you want to, but I think, especially since we've done this before, you can see that happening. What else? You're not done. Philip?
There's another one we talked about.
There's another one over here, yeah. Mrs. Ford, how do you know it's up there? Well, first of all, I know there has to be something over here. You don't just have a blank space in your curve, unless it's a radical or something weird. But I know it has to be up here, because if it were down here, remember, this is an end behavior asymptote. So that means as we head off the page, we're gonna approach it. So I'm either gonna approach it from the top, or I'm gonna approach it from the bottom. Well, if I approached it from the bottom, what would have to happen right here? I'd have to have another x-intercept, and I don't have one. This is the only x-intercept I have. That's why I like you to plot the intercepts first, because that's the only places that you can cross the axes. Those are the only places. Okay, all right, why don't you try the next one by yourself? See how far you can get with the next one. Same exact thing. What's a little unusual about this?
The top doesn't factor.
The top doesn't factor. Now the bottom does, and I would go ahead and factor it. Did you do that? Why would you go ahead and factor the bottom? You know you're not going to be able to cancel because the top doesn't factor, but what's the bottom going to give you? Well,
sorry, asymptotes.
I'm going to get the vertical asymptotes. It impacts that intercept, but I'm going to get the vertical asymptotes, which there are two of them, right? Now, is there also a horizontal asymptote or an end behavior asymptote? Why, yes. Don't we have right here? Don't we have one? There's no holes, obviously, we didn't cancel. Is there a y-intercept? Well, yes, there is a y-intercept. It is, what, -1/5? Are there any x-intercepts? Is there any value of x that would make this fraction equal 0? No, I mean, if you think about it, if you said, okay, I need this to be 0, you would multiply this over and it would be gone, and you'd be left with this equation right here. When you solve that, what happens? It's imaginary. So there are no x-intercepts. Okay, so I need you to formulate a picture from this. What do you think? Do you think it looks like Braden?
You just plug in.
Okay, so Braden says, I have no idea what it looks like. So I'm going to do what I always do when I don't know what a graph looks like. I plot points. Now, he may not literally set up the chart, but he says, I'm going to plug in 1. And I'm going to see what happens. And I'm going to plug in another number, and I'm going to see what happens. I'm good with that. I'm totally good with that. Does anybody have any, like, just logical or thinking strategy? This will always work, Braden. I do not want to discount it at all. When I don't know what something looks like, this is what I do. I think it's the best thing ever. Madeline, what do you think?
You know, there's a parabola opening down because there's an x-intercept there.
You mean a y-intercept?
Yeah.
Yeah, I don't, whatever the curve is doing, it has to go through that point, right? So that thing is kind of trapped between these two asymptotes. As the curve approaches its asymptote, its vertical asymptote, it's either going to shoot up or it's going to shoot down. And in this case, it has to shoot down because we already said it can't cross the x-axis. So it's going to come down. Now, she said parabola. I don't have any idea. What I do know is whatever it's doing, it doesn't cross the x-axis. Okay. Now, Braden, had you plugged in 1, you would have gotten some point down here, and you would get a better picture than us because you're actually plotting points. But we can kind of logic that out. All right, what about the rest of the picture? What do you think there? Philip?
There's going to be 2 curves going on the top right and top left.
And I want you to think about that, kids. When we say that this is an end behavior asymptote, horizontal asymptotes are a form of end behavior asymptote. When we say that, that means as you go to the ends of the picture, it approaches this. So doesn't it have to be coming in like this? It can't be coming up from the bottom because it can't cross. When you have time, go ahead and type that in here. Not now. We're going to do something that's the coolest thing ever. So not now. But when you have time, type that in on your calculator and see how close we came. Now this shape isn't going to be exact, but that's what it looks like. Okay? What are you so excited about? Well, we're going to do a quick review problem. And then we are going to do something absolutely amazing. All right, so we've got this triangle. And I'm not like plotting these points. I'm just plopping them up there. And we're going to find the area of the triangle. And I said, first of all, using the dot product. Oh gosh, what am I talking about? Do we remember that the area of a triangle is 1/2 side, side, sine of included angle? Do you remember that? So I'm just arbitrarily going to pick a couple sides. Can I find the lengths of these sides? Oh, sure, that's easy. In fact, I think because I'm going to need to do the dot product, I think I'm going to go ahead and find the coordinates of vector CS, and then I'll just use its magnitude for the length. So what are the coordinates of CS? 3 and 9, perfect. So the magnitude of that would be 80.
Should be -9.
Oh, is it -9? Oh, yeah, thank you. That's important, thank you. So the magnitude of that is still going to be root 90. I'm not going to reduce that. Is that okay? What about CH? What are the coordinates of CH? 4, -1. So the magnitude of that is root 17. You okay with that? Now I need to know what this angle is. I know this side is root 90 and this side is root 17. We just found that out. Now I need to find that angle using the dot product. Anybody remember how that works? remember that the dot product, well, do you remember how to find the dot product? What's the dot product here gonna be? 12 plus 9, so 21. But the dot product is also the magnitude of the first times the magnitude of the second times the cosine of the angle between them. Remember that? So the cosine of the angle is 21 divided by the square root of 90 times 17, whatever that is. Because this is the dot product. So 21 equals all that, so I'll divide, and that's the cosine of the angle. Tell me something, make me feel good. This is starting to come back, I'm trying to recognize some of this stuff, right? It's only in the last chapter, okay. Now, on my calculator, can I find the angle? Then, okay, so let's just go ahead and do that. So second cosine 21 divided by the square root of 90 times 17. Now let's not round it off or anything. Did you get 57 point something? Now that's this angle. So when I'm finding the area, I'm going to take 1/2 times root 90 times root 17 times the sine of what's on my calculator. So let's do that. So 0.5 times the square root of 90 times the square root of 17. Oops, I need to close the parentheses. Times the sine of my answer. Goodness, I got 16.5. So I'm using a lot, this is good exam review, I'm using a lot of past concepts here. We found the coordinates of these two vectors. We remember the area is 1/2 side sine. So we found the sides, and then to find the angle, we use this strategy right here. Did everybody get 16.5? Now, this is the coolest thing ever. I want you to take your two vectors that we found, right here, these guys right here, and I want you just to cut them out, and I want you to paste them in the determinant. So we don't need the parentheses, of course, but we do need those negatives. Just paste them right there. So I took the two vectors, CS and CH, and I put them in a determinant. All right, let's evaluate the determinant. So that's -3 plus 36, 33. What's half of 33? Guys, oh my gosh, isn't that the coolest thing ever? So to find the area of the triangle, we don't have to do all this stuff. All we need is right there. If you build CS and CH or whatever they are, make a determinant out of them, evaluate the determinant, and cut it in half. Area of a triangle is always 1/2, always half of something. You will get the area of the triangle. It is possible, depending on how you arrange these original vectors, it's possible that when you evaluate the determinant, it will be a negative number. Can you see how that could happen? I mean, obviously, you could get a negative. If that happens, just drop the negative, just ignore it. We want the absolute value of the determinant divided by 2. Oh, you guys.